All right, everybody. In the words of Carol Baskins, hey, all you cool cats and kittens, are you guys ready to do some more organic chemistry? Outstanding. So, we left off last time talking about the first of the four effects that we can look at regarding different structures to tell if they're more acidic or less acidic than comparable species. All right. So we went over the element effect. All right. We're going to go over the other three here. Next one is called the inductive effect. That's a messed up F right there. There we go. All right. Okay, so this one's a little bit different and a little bit similar to the element effect. Here's how they're different. Here, we're not looking at the atom directly attached to the proton that you lost. Instead, we're looking further on down the molecule. All right. Here's a good way to explain it. All right. The best way to explain it is to show you through example. All right. Let's say we have these two compounds. All right. They're very similar, right? The only difference is one of them has a fluorine on it and the other one doesn't. All right, so we can use the element effect here to figure out which one of our protons we're most likely to lose, and we can draw our conjugate bases, right? And I think hopefully you should be able to tell that over here on this left structure, we're going to be losing the H off of the oxygen, right? Because oxygen can better handle a negative charge that would be left over. It can handle that better than a carbon could. All right. Same thing over here. The element effect is going to tell us that we're going to lose the H off of the oxygen. All right. So there's our two conjugate bases. Remember, we want to look at our conjugate bases and we want to see which one is more stable, right? Well, in the previous examples, we saw that we either had like a negative oxygen or a negative carbon, or maybe a negative nitrogen or a negative carbon, or something like that. Two different negatively charged atoms to compare. Here you see that in this structure we have negative oxygen. In this structure we have negative oxygen, right? So there's no way that you can use the element effect to tell which one of these is the most stable, right? You have to look at the rest of the molecule. Right? Here's where the inductive effect comes in. When we're talking about inductive effect, what we're talking about is when you have particular atoms or groups of atoms on a certain part of the molecule and they can inductively either sort of pull electron density their way or push it away, right? And specifically in this case, what we're going to be doing is we're going to be looking for electronegative atoms. And you'll notice I put the most electronegative atom up here. That's fluorine, right? Here's what we're going to see. All right, this fluorine has a tremendous pull on electrons, all right? So what it's going to do, it's going to take this negative charge, right? And this negative charge, don't forget, even though I didn't draw them, they're still there, is due to an abundance of electron density, right? What fluorine can do, it can sort of pull some of that electron density toward its way, right? It's not going to like completely yank the electrons away or anything, but it's just going to cause that electron cloud to drift a little bit over the course of the molecule instead of staying all bunched up on that oxygen, right? The difference with the structure on the left is there's absolutely nothing over here on this side of the molecule that can pull inductively that negative charge its way. That negative charge is entirely focused right on this oxygen right over here, right? And what did we say about negative charge? What did we say about electrons? We said this previously in another chapter. They like to spread out, right? Electrons are happier when they can spread out. A good analogy is if you have a piece of bread, right? Let's say you're trying to make a peanut butter sandwich, all right? You get a piece of bread, you get some peanut butter. You could take this peanut butter and you could put the whole glob in one little corner. And, you know, while everybody's different, I would suspect that you probably would not be very happy with that, right? But If you spread the peanut butter over the course of the entire piece of bread, then you're in a happier situation, right? That's more pleasing, right? That's basically what the molecule is thinking here with regard to the electron density. Electrons like to be spread out, okay? So this structure, this conjugate base, is going to be more stable. If it's more stable, that means that this guy is more likely to lose a proton and, as a result, is more acidic. Okay? So spreading out charge helps to stabilize the entire species. Now let's take a look at another one. Let's take a look at this one. Alright, it's going to be pretty similar. Going to keep it a 2-carbon unit. This time, over here, I'm going to have a Br hanging off the edge of it. In this case, I'm going to have a Cl. And again, just like last time, I think you can use the element effect to figure out that we're going to lose the proton off the oxygen. So, boom, there's our first conjugate base. And here is our second one. Whoops, I drew an H. That's a mistake. Let's get rid of that. There we go. All right, so again, we see, the two conjugate bases are really, really similar. It's a little bit different than the last example, though, right? In the last example, one of the structures didn't have anything that could inductively pull. In this case, on the left, we have a Br. That's electronegative. On the right structure, we have a Cl. That's electronegative. So, in each case, there is an inductive effect, sort of pulling some electron density over the course of the molecule. However, they're not the same, though, right? If you look at Br and Cl, what you can do is you can apply a periodic trend, all right? Remember your periodic trends. Where in a row do we get more electronegative, right? Excuse me, not in a row, sorry, in a column. Because Br and the Cl are in the same position row-wise, but they're not the same position in a column. My mistake. Remember, as we go up a column, we have increasing electronegativity. All right? So if you look at a periodic chart, you would see that even though they're both pretty electronegative, Cl is definitely more electronegative than Br, right? So due to electronegativity, the Cl is going to exert a little bit stronger of a pull here on these electrons as opposed to the Br in its respective example. All right? Now you may ask, well, when we talked about the element effect, the size of the atom had an impact, right? We saw that the size of Br overcame its electronegativity, and the HBr was actually more acidic than HCl. It would be very good to consider that, but I can tell you, you don't have to, because size in the inductive effect has no bearing at all. It's all about electronegativity, right? So, since Cl is more electronegative than bromine, that means this guy is more stable. And this guy right over here is going to be a little bit more acidic than the one on the left. Okay? All right. The inductive effects especially gives you the opportunity for a number of interesting situations to look at. Right? Here's an interesting one. And this might make you think a little bit. Hopefully it will, because thinking is good. Come on, there we go. All right, let's say we have this guy versus this guy. All right. So again, two very similar compounds, except hold on, there we go. I want to make sure the number of carbons are the same, just for, try to keep everything as similar as possible. All right, so these are pretty similar. The only difference between these two is that there's a fluorine in a different position in each one, right? Let's go ahead and draw the conjugate bases, and then we'll take a look at them. I think hopefully, again, you can use the element effect here to figure out that you're going to lose an H from your nitrogen, right? So you're going to have that. And that's a mistake there. You're not supposed to have an F there. You're supposed to have an F here. There we go. All right, so here's an interesting question. It's a bit of a thinker. Which one of these is going to be the more stable conjugate base? I did this in class today with my Monday group, and there's actually a really good logical argument for either one of these. Only one of them is right, though. All right? In both cases, you are going to have an inductive effect, right? On the left, fluorine does attract some electron density over the course of the entire molecule. In this case, on the right, it spreads it out, not over the entire molecule, but sort of over here. So there's a couple of things to consider here. One course of thought here is that, well, in the first molecule over here, the fluorine is further away. That means it draws the electron density over a larger area than this fluorine does, right? So if you're thinking about it that way, the structure on the left would be the more stable conjugate base, right? However, here's another way to think about it. With this guy, the structure on the right, the F is closer, and that means sort of its quote-unquote magnetic effect is going to be more powerful, right? Since it's closer, it can draw more of the electrons from that individual spot on the nitrogen. So, it's a conundrum here, right? Is the more stable situation to have more electrons spread over, a smaller amount of the molecule, or is it more stable to have a smaller amount of electrons spread over the entirety? And it's a very good question. I could see an argument either way. I can tell you, though, that this guy is more stable. Yeah. Because F is closer, it's able to sort of have an effect on a larger group of electrons. And the really important thing is not necessarily that they're spread over the whole molecule, but that they're spread off of just that one little singular nitrogen. So while they would both be stabilized, this guy is the more stable one, and that means this one would be slightly more acidic. All right? So all other things being equal, if your inductive electronegative atom is a bit closer to your electron source, it's going to have more of a pull and more of a stabilizing factor. Here's an interesting one. I don't know if this is exactly the one we did in class, but it's similar. All right. This one's pretty similar to the last one, except our electronegative atoms are not the same, right? And then in one case we have a Cl, one case we have an F. If we draw the conjugate bases, they look like this. All right, and so here's a bit of a conundrum here, right? This guy is definitely closer to your electron source, the nitrogen, right? So, we said previously that all things being equal, that's a better, more stable situation. However, all things are not equal because fluorine is a more electronegative atom than Cl, right? So which one wins? The answer, da-da-da-da-da-da, I don't know. This is a bit of a conundrum. This is going to be a case where you would probably, to get a really accurate answer, you would just want to look up their pKa values. So we can't always get a pinpoint prediction on the structure. If we have a case like this, it's kind of impossible offhand to know, whether the proximity of the Cl is going to dominate or the electronegativity of the F is going to dominate. That case is kind of situational. So don't worry, I won't give you one like that doesn't have, a discernible answer. But I just wanted to show you that there are going to be some situations that we can't fully predict. Here's one that we can. Let's try this one. And this is also a unique situation that we haven't seen yet. All right, so here, let me just go ahead and draw these so we can go ahead and have them ready to look at. So again, we have negative nitrogens. Do. I'm gonna add sound effects to make everything fun. La 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 la. All right, so this is a little bit different because, again, here we have fluorine. Fluorine, we know, is highly, highly electronegative. In fact, it's the most electronegative atom. And it's in closer proximity to your nitrogen than these other guys, right? These are both iodines, which we know are less electronegative than fluorine. They are also not as close here to the nitrogen, but they still do have an inductive effect. However, one advantage iodine does have here is that there's two of them, right? There's two iodines and there's one fluorine. So, does the fact there's two iodines outweigh the fact that fluorine is more electronegative and closer? In this particular case, yes, it does. It's only one carbon difference. And also, the electronegativity of iodine is not too much lower. Usually, if there's two electronegative atoms, that will trump a singular one, even if the singular one is a little bit more powerful. I say usually because there are limits, of course. All right? It would be a little bit different if it was... Come on. There we go. It would be a little bit different if we were comparing, something like this versus something like this. In that case, the iodines are so far away from nitrogen, nitrogen can barely feel it. So in that case, this guy would be more stable, right? So you have to use a little bit of common sense. But in similar situations as in the previous example, generally speaking, the presence of more electronegative atoms means higher acidity. All right. Okay, like I said, probably out of the four of these, that's the most, inductive effect is the most nuanced example. Also, it's basically tied for the second most powerful effect. Element effect is definitely the most powerful. Inductive effect and the one we're about to talk about, resonance, they're pretty similar in terms of power. As far as which one's more powerful, it might just be situational. In one situation, resonance might be a little bit more powerful than induction, and another one vice versa. So they're pretty interchangeable as far as power. But basically, resonance does something that is similar that induction does. It basically serves to spread out electron density, right? Remember, electrons, they're happier when they're spread out. All right, let me show you an example. Oh, that's ugly. Let me redraw that. heck, let me start over. You know, I'm not a very neat drawer, but even I have my limits on what's acceptable. Alright. Let's compare that. And let's compare something pretty comparable. Let's compare it to this. Okay? Again, I think you can probably tell we're going to lose the H off of the oxygen. So we're going to get that, and we're going to get this. Alright, and in this example, I'm going to just go ahead and draw all the unshared pairs, because that might be useful to seeing how things go. Alright. Okay, so if we look at this, you know, the negative charge in each case is on oxygen, so we can't use the element effect to figure this out. If we look at induction, I mean, they both do have inductive effects, right? Each of them has another oxygen that's basically one carbon away. But, again, they're pretty much equivalent to each other as far as induction, so you can't really use that. However, you are going to see that for one of these, we can actually draw a resonance structure, and for the other one, you can't. All right? You may want to pause it right now to consider this and try to draw it on your own before I draw it. See if you can draw a resonance structure for either one of these structures, for either one of these species, right? I want to give you a hint. You can only do it for one of them. For one of them, you're not going to be able to. All right, hopefully by now you've tried it. All right, so I'm going to show you. If you look at the structure over here on the left, you can actually take these. Remember, the electrons you can move in resonance structures are unshared pairs and or pi electrons. You could take this unshared pair and swing it into a double bond with that carbon. That's going to give that carbon too many electrons, so it in turn has to swing a pair of electrons over here. So, for this one, we can draw a resonance structure that looks like this. That means you have some electron density that's a little bit spread out and floating all the way in between this area of the molecule. If you try to do that with the other one, you're going to run into a roadblock, right? You could try to bring a pair of electrons down like that, but here's where you run into a problem. This carbon, don't forget, I'm going to draw, this is skeletal structure, so don't forget this has an H, all right? That's going to give this carbon right over here too many electrons, and there's no way for it to give up a pair without breaking a sigma bond. And we know breaking sigma bonds is a big no-no in resonance, right? So this one has no resonance structures. There's no way to use resonance to help spread out electron density, while over here there is. So that means this situation is going to be more stable, and this guy is going to be more acidic. Very good. Again, I just want to, it's in my automatic memory from doing this for so many years. I want to say, does that make sense? Do you guys have any questions? Blah blah blah. And I realize I can say that, but I'm going to get silence. And eventually I'm going to sound crazy like I'm talking to myself. Actually, I might just talk to the voices in my head as I go along. Might make it a little bit easier. We'll see. Plus, it'll be very entertaining for you guys. Ha 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 ha. Alright, so that's basically how the resonance effect works. There's one more effect, and that's called the hybridization effect. This one is the weakest out of all four effects. So it's basically the last one that you look for. All right? And as you might guess, in this case, we're going to be looking at the hybridization of different atoms, right? So remember I told you in the last chapter, you're going to need to get where you can just look at an atom and immediately say, sp3 hybridized, sp2, sp, right? Here's an example of where you're going to do that. All right, let's compare these two molecules. Whoops, that's CH3CH3 versus CH, CH, and the C's are in triple bonds. Draw it like that. All right. All right, you might notice this one's a little bit different looking because, hey, we don't have any electronegative atoms here. We don't have any nitrogens or oxygens or halogens or anything like that. Just C's and H's. All right. Well, let's see where we would lose a hydrogen from. We have no choice but to lose a hydrogen in each case from carbon. I purposely made these symmetrical so it'd be easier to process. You know, CH3CH3 is symmetrical. It doesn't really matter which side we choose. I'll just lose one off the right side. All right, so if we did that, we would have an extra pair of electrons on that carbon, and it would be negative charged. All right, same thing can happen over here. Again, it doesn't matter which one I pick in this case because it's symmetrical. You would end up with that. All right, so we've got the conjugate bases. Now we got to figure out, okay, which one's more stable? And here's where being able to predict the hybridization is going to be important. All right. So let me backtrack a little bit. Let me talk, and this is like I told my class today. This part is a little bit abstract to some people, and so they have a little bit of a hard time getting their head around it. So if you need some clarification on this, please don't hesitate to ask. All right. What I want you to think about right now is I want you to consider individual orbitals, individual s orbitals, and individual p orbitals, even before they hybridize. All right? Okay. Ask yourself which one of these orbitals is closer to the nucleus. Hopefully, if you remember from Gen Chem, you'll be able to realize that s orbitals are closer to the nucleus than p orbitals are. Okay? That's going to be important. Also, when we look at hybrid orbitals, we can determine something called S character. S character basically means what percentage of the hybrid orbital is composed of S in any given situation. So for example, if we had an sp3 orbital, what percentage of an sp3 orbital is made out of S? Well, it's 1 part S, 3 parts P, right? So 1 in 4 parts of this orbital are made out of S, so it would have 25%, S character. All right? Keep that also in the back of your mind. Let's go ahead and assign hybridizations to each one of these carbons, each one of these negative carbons. This guy over here on the left, it's got 4 groups around it, 1 carbon, 2 H's, and an unshared pair. We said if you have 4 groups, it's sp3. Okay? And the structure on the right, you have 1 carbon bonded and 1 unshared pair. That's 2 groups, so it's sp. All right? If we look at S character, we already said sp3 has 25% S character, right? SP, hopefully, you'll be able to calculate, you know, for all you math majors out there, that it has 50% S character, right? So sp orbitals have higher S character. All right, so think about this. Which one of these hybrid orbitals more closely resembles a pure S orbital? Is it sp or sp3, right? Well, since sp has higher S character, that means it's going to more closely resemble just a pure S orbital. All right? And we already said that S orbitals are closer to the nucleus than p orbitals are, right? So we can also infer that hybrid orbitals with higher S character are closer to the nucleus than hybrid orbitals of less S character. So sp orbitals are closer to the nucleus than sp3. Why is that important? Well, you have electrons in these hybrid orbitals. Electrons are negative, right? Ask yourself, what's the charge of a nucleus? Nuclei have what in them? They have neutrons, which are 0, and they have protons, which are +1. So overall, a nucleus is positive. Think about it. You have electrons that are negative and a nucleus that's positive. What do opposite charges do? They attract each other, right? So bottom line, electrons that are closer to the nucleus are happier than electrons that are further away. That means the electrons that are in the sp hybridized orbital right here are happier than the electrons that are in this sp3 orbital. That means this guy is going to be more stable, and overall, this one is more acidic. So yeah, you can see there's a lot to process with that one. There's a lot of little different things to consider.
Here's some information.
Okay, my phone started talking to me randomly. That was weird. So please excuse that. But yeah, the higher the S character, the more stable electrons found in those orbitals are. As a result, the parent molecule is more acidic. I do want to reemphasize, this is the weakest effect. So if you had something like something like resonance or induction that was playing a part, then that would totally change the story, right? If our conjugate base, if our conjugate base looked like this instead, right, then, obviously this one would be more stable because it would have an inductive effect that's more powerful, right? But all other things being equal, yeah, higher S character, more stability. Alrighty. Those are the 4 structural effects, right? Let's do an example where you have to consider more than one of these, all right? What we're going to do is we're going to take 4 compounds, and I'm going to try to space these apart so we can do them fairly easily. Let's say we had that. That. Whoops. Made a mistake. Alright, let's say we had these 4. Alright? Okay, well, first of all, and what we're going to do here, by the way, is we're going to rank these in ascending order of acidity. So, we're going to rank them 1 through 4. So, the number 4 equals most acidic. Alright? And since number 1, I don't have much room on this drawing thing to draw every single conjugate base. And number 2, I would like you to have an exercise on doing this on your own. I'm going to ask you to draw the conjugate bases on your own. Alright? I will give you a hint. In this case, and in this case, you could probably lose the hydrogen from more than one spot. Alright? As long as you pick, one of the right ones, then it's okay. Alright, so as you're doing this, keep a couple of things in mind. We want to analyze these conjugate bases that you draw going in order. Alright, so the very first thing we want to do is look at the element effect to figure out, is there anything that's obviously more stable than the other based on where the negative charge is. Then you would look at the resonance effect and the inductive effect to determine if there's any way you can spread that charge out. Lastly speaking, you would look to see if there was a case where you would need to look at the S character of a particular species to distinguish stability. All right, so I'm going to have you guys do this one on your own, right? Hopefully we'll be able to talk about it in our weekly meeting in class, and if you have questions about it, we can talk about it there. All right, until next time, that ends this video. All right, talk to you later. Bye-bye.